For this problem, I'm going to use some old material that we know, something from Chapter 2, and how to find different speeds or velocities as a ball is dropped from rest as it's moving through certain distances. And once I know those speeds, then I'm going to make a table, and I'm going to have us calculate all the different energies that are involved in this chapter. And I'm trying to show that there is something called conservation of mechanical energy. And conservation of mechanical energy comes when we add up the different types of mechanical energy that we know about. So kinetic energy is a mechanical energy, and gravitational potential energy is also a mechanical energy. So that's the point of this little demonstration. So what I'm saying is, if we had a baseball that was held up here, and this building I'm saying is 100 meters tall, and I'm saying it starts from rest. So the velocity up here is at 0 meters per second. So that's its velocity at that height of 100 meters. Then I'm saying, let's look at it at a few different heights. So if I look at here, we're at a height of 75 meters. And then I want to look at here when it's halfway at a height of 50 meters. I want to look at it here when it's at a height of 25 meters. All of these heights are with respect to the ground. I'm referencing the ground. So, and this height down here at the bottom would be 0 meters. Okay? So when the ball has fallen this far, it's fallen a distance of 25 meters. And the formula in Chapter 2 told us how to figure out how fast it's going. So what I'm saying, just for the first part to get some numbers, I'm saying we are going to drop a 0.25 kilogram ball from rest at the top of a 100 meter tall building, period. Find its speed at a height of 75 meters, at a height of 50 meters, at a height of 25 meters, and at the height of 0 meters above the ground. So let me erase that, and then we'll go and we'll calculate these things. So from Chapter 2, we learned this formula: V final squared equals V initial squared plus 2A delta Y. And if we plug in those numbers, so it is V final, which has to be squared, equals 0. We don't even have to write that because it's 0. And then over here we have a plus 2, and we have a negative 9.8, and we have the negative 25 meters. So if you take out your calculator and you calculate 22.13, so V final comes out to be, and remember, when you take the square root of both sides, it's a plus or minus. The velocity will be a negative 22.13 meters per second. And the idea of being the negative here is it's moving downward. And I'm looking at this location right here. If it was at 100 meters tall, and now we're looking at the height of 75 meters above the ground, the ball has fallen 25 meters. So that's why I put a negative 25 for this particular place. So we only want to know the speed. So right at this well, I could put the velocity. The velocity at this location would be a negative 22.13 meters per second. And I want to know what the velocity is when it falls a total of 50 meters. So if I want to do the falling of a total of 50 meters, I don't have to change too much. All I have to do is change this number right here. So if I change that number and make this a negative 50 meters, do it on my calculator, it comes out to be negative 31.30. So this comes out to be a negative 31.30 meters per second. If I want to see what happens when it falls a total of 75 meters, then here I would look for that velocity. And if it's falling a total of 75 meters, I'd plug in negative 75 here. And I'd use my calculator. And I square root both sides, so I get 38.34 negative. Means it's going down. And for the final one, if I plug in what happens when it gets all the way to the bottom, so as it goes all the way to the bottom down to 0 meters, I will plug in negative 100. So if I do those numbers on my calculator, it comes out to be negative 44.27. And that's meters per second. Okay, so my velocity right before it touches the ground is a negative 44.27. Okay, so with this activity, I have all of these different velocities at these different heights. And in the original problem that I wrote on the board, I had said that the mass of this ball, I had said the mass was equal to 0.25 kilograms. So I'm going to make a table here. So for this first one, I'll use the formula kinetic energy. Which is 1/2 mv squared. And for the second one, I'll use potential energy. The gravitational type. And potential energy is equal to m times g times h. And on this last column, I'll talk about the mechanical energy. Which just equals the kinetic energy plus the potential energy. Okay, so I have formulas. So this is basically one of those things that you plug in, and if you just plug it in, what we have is I have the mass for each of these, and I have the velocity of each of these. This is a bit repetitive, but you basically just have to take your calculator and number crunch. So if you did 1/2 times, well, anyways, the first one's 0. So I'll write the first one up here. 1/2 times 0.25 kilograms times 0. Well, this one is 0. And the unit is joules. If I jump all the way down to the bottom, just to show you another formula, I could put this one as 1/2. The mass is 0.25. And the speed is, the velocity is negative 44.27. And I have to square that. So if I do that on my calculator, I'm going to come up with a number, and it's just approximately 250. It's like 240. Sorry, it's 245 almost. It says it's 244.98. So this is about 245 joules. And you do the same thing with this number and this number and this number. So if you fill in those tables, you just have to keep on number crunching, and I'll just go and fill in the table. So you see, we have a bunch of numbers here now. We have 0 joules, we have 61.22 joules, we have 122.46 joules, we have 183.74 joules, and we have 245 joules. As was defined earlier, kinetic energy is the energy of motion. When something is moving, it has kinetic energy. And as it moves faster and faster, it has more and more kinetic energy. So as the ball here is falling, and it's moving faster and faster and faster, these numbers are getting bigger. The speed would be the absolute value of these numbers. Well, as it's getting bigger, you can see that these energies are getting bigger also. So now we go on to the potential energy. So the potential energy says mass times gravity times height. So again, you have to just calculate this particular piece. So if I go and I take the mass of it, the mass of this thing is 0.25, so it's going to be 0.25 kilograms. Gravity is 9.8, and the height is 100 meters. So when I go and I calculate that, this comes out to be 245 joules. Okay? And you have to just keep on doing it with all the heights. So at this particular location, you'd have 0.25 times 9.8 meters per second squared times 75 meters. So again, I'm going to put down the mic and just do these. Gravitational potential energy deals when something is elevated above some reference point. So if I call the ground 0, then anything above that point has this thing called gravitational potential energy. So when I'm very, very high up, I have a lot of gravitational potential energy. And as I go down a little bit, I have less gravitational potential energy. The number went from 245 down to 183. As I go less, the numbers are getting smaller. So I have 122, I have 61, I have 0. So I started with a lot of gravitational potential energy, that's stored up energy, and I ended up with 0. So as you can see, what's happening, hopefully, is there's a give and take. As an object loses one type of energy, this one type of energy started at 245 and went down to 0. And at the same time, this side, the object started from rest, so the object had zero kinetic energy, and then it started to gain some. And what we say is there's something called conservation of mechanical energy, and conservation of mechanical energy means, well, first of all, mechanical energy means just add them up. So add up all of the energies you know about that are called mechanical energy. Kinetic is in mechanical energy, potential is in mechanical energy. So if I add those up, okay, so what you should notice, you should have noticed, as I just said a moment ago, look at the kinetic energy. As the ball was falling, its speed got faster and faster and faster and faster. So the kinetic energy numbers got small, bigger, 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 bigger yet. The potential energy deals with the energy associated with height. So as the ball was falling down to the ground, the energy numbers for potential energy got smaller and smaller. So we had 245, then we had 183, then we had 122, then we had 61, then we had 0. And the mechanical energy is the total energy associated with the system. I got them from just adding 0 plus 245, gave me 245 joules. 61.22 plus 183.75 gave me 244.97 joules. The mechanical energy are numbers all hovering very close to 245. So it's 245 here. This is 244.97. That's 245. This is 244.96. That's approximately 245. This is 244.99. That's extremely close to 245. And this is 245. So all of our mechanical energy numbers are coming out to be almost perfectly the same. The reason why they're not 100% the same is when we calculated their speeds, we didn't write down every single decimal point. So I only wrote down 2 numbers. So because I've rounded these numbers off a little bit, thus these numbers have been rounded a little bit. But I think they're good enough to try to show you the idea that right here, there's something called mechanical energy which is conserved. So we have this rule that says conservation of energy. And in the conservation of energy idea, they say that the total mechanical energy of the system remains the same. So as an object is moving, for this case, the ball was dropped and fell. As the object is moving, it will change one type of energy into another. So you see, all of the gravitational potential energy is going to end up disappearing in this problem. The ball was very, very high up off the ground, and when the ball then went and fell, when the ball hit the ground, it was no longer above the ground, so it had no gravitational potential energy. But all of that energy just didn't disappear and vaporize. It was transformed into another type of energy, and it was transformed into this type of energy called kinetic energy. Okay? So there's a give and take. As one energy goes down, so the potential energy went down, the kinetic energy numbers went up. And we're only studying this when it's moving through the air. Okay? Once it hits the ground, then our problem is over. Once it hits the ground, well, by hitting the ground, there'll be sound. And there's energy associated with sound. So the sound energy will, the kinetic energy will seem to disappear after the ball hits the ground and eventually stops. It didn't just disappear, it was transformed into some other type of energy, which is called sound energy, which is in a future chapter in physics. If I continue with this idea for this particular problem, I could come up with a word problem which says behind me, we will drop a ball from rest off of a tall building. I don't even say how tall the building is. And then I say, find its speed after it has fallen through 75 meters. So for this particular case, it's almost as if we're looking right here. This was the last problem we just did. This right here is 100 meters tall. If it falls through 75 meters, then it fell through this distance right here. So it's going to fall through that distance. So you see, that's what happens when the ball falls through 75 meters. We've just dropped this thing down 75 meters. And we've already done this problem a different way using some old things. Now let's try to do it using the new formulas, and let's try to see if we can come up with this number. Now when we use conservation of energy, it's only going to tell us a scalar. It will not tell us the vector piece. So what is conservation of energy? It basically means that the total energy at the beginning is equal to the total energy at the end. We're pretending there's no air resistance. So what I'm saying is the energy total at the beginning will equal the energy total at the end. Okay? What is the energy total? Well, we always have two possibilities of energy. In this case, anyways, we have mechanical energy. We have kinetic energy. So the kinetic energy at the beginning plus the gravitational potential energy at the beginning. And that could equal kinetic energy at the end plus potential energy, gravitational, at the end. So I put subscripts here for O for the beginning and F's for the final. And what is kinetic energy? It's this formula, 1/2 mv squared initial plus, what's potential energy's formula? Mass times gravity times height initial equals kinetic energy again, 1/2 mv final squared. Potential energies again, mgh final. So before we plug in any numbers, I just want you to look at the formula and notice that there's an m in each one of these particular pieces, okay, in each one of these particular terms. So you see, in this particular example I just gave you, I didn't say what the mass is. So a few minutes ago we did another problem where I said there was a 100-meter tall building, and I said that we were going to drop a ball from 100 meters and look at it every 25-meter fall it went through. But this is I didn't say this was the exact same. I said we're going to drop a ball, but I don't give the mass. I'm saying we're dropping it from rest off of a tall building. Well, we can still use these ideas because this ball was dropped from rest, and this ball did fall through 75 meters. So my point is, for this specific problem, I have not given you the mass of the ball. But we don't need it. If you look carefully, mass is in each one of these terms, so this thing called mass will cancel out. So the mass is there, 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 and there will cancel out. And if they cancel out, that's good, then we don't have to use them. So what I did is I basically just divided each term by m. So if I divide every single term by m, then the m's just go away. And now I can plug it in. So if I plug it in, I would plug in 1/2. Now the initial velocity of this ball was from rest, so I'll say 0 meters per second. Okay. Plus, gravity is the number 9.8, and the initial height of it, I don't exactly know what the initial height of it is. I can call any height whatsoever a relative height of 0. I can reference everything with my height of 0. So I could call this thing here, I could call it any number. I could call this 75 meters. Okay? I could base it off the old picture here, and I could call it at 100 meters. But whatever I call the first one, I have to make sure the second point will be lower by 75 meters. So it's up to you what you want to call this thing. Some students will call it 0. They'll always call their starting place 0. Some students in their mind says, if I have to have it drop through 75 meters, why don't I just call the maximum height 75? I'll just use the numbers right here that are in the table. I'll call this height right here 100, and I'll call this height right here 25. So I'll say that this is at 100 meters, okay, and that's going to equal 1/2 And the mass of this thing, we don't know. We've already canceled it out, I mean. And we want to find V final, and that's squared. Plus, I need a little bit more here. Plus, gravity is the number 9.8. And the height final, I'll just have to squish it in. The height final would be this number 25. So I'll put that right in there. Okay. So with this particular problem, what I'm doing right now is I'm saying, let's say we're starting here, and let's say we're ending here. And we're going to go from our starting point down to our ending point. And using this formula here, this will help us figure out what it's going to be. So anything times 0 is 0, so this is gone. 9.8 times 100, that comes out to be 980. The units are meters squared over seconds squared, equals, this is 1/2 times V final, which is going to be squared. And this is going to be plus 9.8 times 25. Well, it's difficult to continue going down because I've run out of space. So if I go to the top here, I'll just erase the top for a moment. I'll rewrite the last line. So the last line down here was 980 meters squared over seconds squared equals 1/2 V final, which was squared, plus 245 meters squared over seconds squared. If I simplify that, I will subtract 245 from both sides. That's gone. And if I take this 980 minus 245, this becomes 735 meters squared per second squared, and that equals 1/2 V final, which is squared. Now I will multiply both sides by 2 to get rid of the 2 in the denominator here. So it becomes 1,470 meters squared over seconds squared, and that's V final, which is squared. And now to solve that, I need to take a square root of both sides. And once I do that, I will have a number on my calculator screen. That comes out to be 38.34. So if you notice over here, when you take a square root, you have a plus or a minus sign in front of it. So that happens by itself. So we could technically say that this would be a minus number. But this value is exactly the same as what we calculated when we just talked about dropping the ball and looking at it every 25 meter increments. So we had said when it fell down 75 meters before, we said the speed would be 38.34. Well, now you see it done without using any old formulas from Chapter 2. Now you see it done using only the formulas from Chapter 6 for the conservation of mechanical energy. And again, we're pretending that there's no air resistance. Okay, so this is called conservation of mechanical energy using conservative forces.